a D, your deterministic simulating Turing machine, and that'll have 3 tapes. And these tapes are called the input tape, which is sort of pretty obvious. Simulation tape, well, it's not so clear. I'll explain what that means in a minute. And a third tape called the address tape. And it's probably even less clear. And I'll explain what that is in a moment as well. So we have 3 tapes. Okay. Now the input tape contain, well, as you can guess, the input string to the Turing machine that's placed into the input tape, and then it doesn't change. Right? So the input tape is effectively fixed. The input string goes in. In this case, it's just 0010. So the input string goes in, and it doesn't change; just stays there. Okay, stationary in a sense. All right. Now, perhaps I'll go. I need a few remarks. You may be saying, well, this is not. It's got 3 tapes. This Turing machine is not a standard Turing machine. Standard Turing machine has 1 tape. Well, we can use the theorem we've just done before, well, a bit before, theorem 3.13, which says that a multi-tape Turing machine is equivalent to a single-tape machine. So we could, if we wanted to, we could translate, if you like, we could construct a single-tape machine that does these, with these, that is equivalent to this, to D, with these 3 tapes. We could do that, but it's just easier to think and to operate with these 3 tapes. So let's do it that way. So our D will be a 3-tape machine because it's just easier to work with. Right. Okay. So how do these 3 tapes work? What are they doing? Well, I've already explained what tape 1 does. Right. It just contains the input string, and it's never altered. Right. So that's pretty easy. Now, what's tape 2? Well, effectively, here's your tree, right? Your computation tree for N, your non-deterministic Turing machine, and choose a particular branch, from the root node, down to down to the root, I guess. Okay. So you choose like a particular path, if you like, a branch, from the root node down to the leaf, I guess. And that path, as you go down node by node in that path, from the root node to the leaf node, along that path, down that branch, same thing, effectively. At each node, you're performing a computation. You're doing a step. In the Turing machine is executing a single step from node to node, changing its configuration from one node to the next. Okay. So that for that path, its string will be changing, like the configuration. So in effect, what this is the second string. Is if you think about it, it's just the configuration at that given moment of that path. I think that's right. Okay. So let me say that again. So the second string contains the configuration at a particular step. So it'll change every step. It will change as you go down that path from node to node in that path. In that branch of your tree, the tape 2 contains the configuration at a particular node. Okay, at a particular node. It's that particular node in that branch's configuration at that moment. Okay. All right. And the third tape contains the address of that node in the tree. Okay? So you imagine this pre-existing tree, this computational tree that you know exists from the non-deterministic Turing machine. So imagine this this N has done its thing. It's created this tree of computational tree. You know what all the configurations are at every node in the tree. There's this bushy tree, if you like, let's say. Okay, and every node in that tree, you can give an address that identifies the node. You give me the address, I can find the node in that tree. Okay, so this third tape contains the address of a particular node in the tree. All right. So now let me summarize what the three tapes are about. The first tape doesn't change. It contains the initial input string. Simple. Second tape contains the configuration at that node in the tree. Okay? At a particular node in the tree. And the third tape contains the address of that node in the tree. Now I need to explain to you how you calculate that address. It's pretty easy, but I hope you got the big picture. Okay, all right. Now, okay. Now I found this a bit vague. That's Sipser. Okay. So Sipser, this is word for word from Sipser's text. So tape 2 contains a copy of N's tape on some branch of its non-deterministic computation. Now, is that the same thing? N's tape. What's on the tape? Okay, so it's not. Okay, so what I've said is incorrect. Okay, it's just the tape. It's what's on the tape. It would be N tape on that particular branch. And our configuration is more than the contents of the tape, right? It's also the current state, and the other thing was the header positions. Okay, so I take that back. It's not. So this is the contents of the tape at along that as it goes down that branch. So this is the contents of the tape when the computation is at that node in the tree. Okay, it's not. It's the contents of the tape. It's not the configuration. Sorry. Okay. Thinking real time a bit here. Okay, now tape 3. That just gives you the address of where your node is, where you are in your computational tree. Because remember, each node each node has its configuration, and from that. And the transition function, you can figure out what the next node will be, what the configuration will be for the next node, using the current node, the current configuration, and pop the necessary parameters into the transition function, and then you can calculate what the configuration will be for the next node, the child nodes, right? All right. Okay. Now, how to represent the data on tape 3? In other words, how to calculate the address? Well, I'll skip Sipser. I'll just give it to you simply. Okay. Imagine you look at all the transition rules, and you have a look at. What's the greatest amount of splitting? Like you look at all the transition rules, and you look at the right hand side, and there will be when non-determinism occurs, there will be splitting. You'll have more than one choice. Okay, so look at all the rules, and And for each case where there is splitting, so where there's non-determinism, in other words, where you have a choice, have a look. How many choices do you have? And for each rule where there's non-determinism, find that number. How many choices do you have? And then find